Training an artificial intelligence model ultimately boils down to a massive optimization problem. We give the model a target, measure how far off its predictions are, and define that error as a loss function. The goal is simply to find the absolute lowest point of error on that landscape. If we only have a single parameter to adjust, this is straightforward. We use standard single-variable calculus to find the derivative, which tells us the exact slope of the curve at any given point. That slope acts like a mathematical compass. It tells that single parameter exactly which direction to step and how large a step to take to move closer to the bottom of the curve where the error is minimized. But modern deep learning models don't have just one parameter. A large language model or image generator contains millions or even hundreds of billions of separate weights and biases that all need to be optimized at the exact same time. Calculating the individual scalar derivative for every single one of those billions of parameters, one by one, would stall even the fastest computers. We need a mathematical framework built from the ground up to handle massive, multidimensional scale. To manage the scale, we borrow the structural tools of linear algebra, which gives us a standardized way to organize high-dimensional data. Instead of tracking billions of isolated variables, we group them. We pack single-dimension lists of parameters into arrays called vectors, and we stack those vectors into two-dimensional grids called matrices. Looking at this least squares loss function, equations 5.75 through 5.77 condense millions of data points into matrix variables. Panning down, equations 5.80 through 5.83 compute partial derivatives for every item simultaneously, resolving into a single gradient vector. Linear algebra builds the grid to organize the data, but it can't find the path to the lowest error on its own. To actually optimize a neural network, we have to marry that grid with multivariable calculus. This strict intersection of multivariable calculus and linear algebra is known as matrix calculus. The central engine of matrix calculus is the Jacobian matrix. It is a highly structured grid that holds all the first-order partial derivatives of a vector-valued function. In a neural network, the Jacobian calculates how a tiny change in any input variable affects every output variable, tracking these overlapping relationships simultaneously. This diagram shows the mechanics. The colored blocks represent isolated partial derivatives computed across different dimensions. Instead of handling them separately, they are collated into a single tensor on the right, providing one unified mathematical object to guide the model. By capturing all partial derivatives at once, the Jacobian provides the exact multidimensional trajectory the entire neural network must take to reduce its overall error. While the Jacobian tells us which way to step, another structure called the Hessian matrix evaluates the terrain itself. The Hessian contains all second-order partial derivatives, allowing it to calculate the exact curvature of the loss function. The Jacobian acts as the compass, providing the direction, but the Hessian acts as the brakes. By mapping the curve of the slopes and saddle points, the Hessian prevents the model from taking too large of a step and overshooting the target minimum entirely. Of course, neural networks are rarely just a single set of inputs and outputs. They are built as deep layers of nested functions, where the output of one layer immediately becomes the input of the next. To find the gradient across these nested layers, matrix calculus scales up the standard chain rule. Instead of multiplying single numbers, we multiply entire Jacobian matrices together, layer by layer, starting from the final output and moving all the way back to the initial input. This continuous backward chain of multiplying Jacobians is backpropagation. It is the exact mechanical process that distributes error corrections across millions of parameters simultaneously. This mathematical theory directly dictates physical hardware design. The reason matrix calculus dictates modern AI efficiency lies in how microchips actually process information. Standard processors read equations sequentially, one after another. But by structuring our calculus inside rigid matrices, we can feed those entire grids of data into graphics processing units, or GPUs, which are explicitly designed to execute thousands of calculations in parallel. Matrix operations like dot products and element-wise additions bypass sequential bottlenecks entirely. These math rules translate directly into the high-speed code running under the hood of deep learning libraries like PyTorch and TensorFlow. If we were forced to calculate multivariable optimization without the structural grids of linear algebra, training a deep neural network would take centuries. Organizing high-dimensional optimization into parallel operations is what makes training modern AI physically possible.